A beam of sunlight takes 8 minutes to cross the vacuum of space. When it strikes the upper atmosphere, that light undergoes a physical reaction. In a true vacuum, light travels in a perfectly straight line at its maximum possible speed, nearly 300,000 kilometers per second. It will maintain that trajectory and velocity indefinitely. But the moment that light enters a physical medium, like the gases of our atmosphere or a pool of water, its path physically bends. This change in direction is called refraction. The mechanism behind this bending is purely physical. As light leaves air and hits water, the denser molecular structure forces the wave to abruptly slow down. Physicists measure this drop using the refractive index, a precise ratio between the speed of light in a vacuum and inside the new material. Every optical illusion you see, a pencil broken in water, or heat waves off a road, is light hitting a speed bump. To understand exactly how these speed bumps work, we have to isolate the light in a controlled environment using a solid glass prism. White light is actually a composite. It is a tightly packed collection of completely different wavelengths traveling together as a single beam. Because each color has a unique wavelength, the dense prism affects them differently. Shorter wavelengths slow down the most, bending at sharper angles inside the glass. This process, called dispersion, separates out the hidden wavelengths to produce the full visible spectrum. Color is not a pigment painted onto the light. The colors are physical dimensions of the waves themselves, revealed only when the light is forced to slow down and bend. We can actually observe these exact laboratory physics playing out on a massive scale in the atmosphere. During a storm, millions of individual raindrops are suspended in the air. Each one of those spherical drops operates as a microscopic prism. This diagram shows sunlight entering a drop and refracting, dispersing into its spectrum. Reaching the opposite side, it undergoes total internal reflection, bouncing back and exiting. Because of internal geometry, violet light always emerges at 40 degrees and red at 42 degrees. This diagram illustrates how multiple drops align to reach your eye. A higher drop sends only its 42-degree red light to you, its violet passing below. Conversely, a lower drop aims its 40-degree violet light directly at you, sending red over your head. A rainbow is a massive three-dimensional optical alignment. You are seeing millions of natural dispersion engines, all refracting specific wavelengths of light into a single precise focal point, your eyes. This interaction between light and matter also answers another basic question: why a clear, dry sky appears blue instead of black? The atmosphere is filled with free atoms and molecules. When light hits these particles, the particles absorb the energy and immediately radiate it back out in every direction. This process is called scattering. The size of the particle determines which color gets scattered. The nitrogen and oxygen molecules dominating our atmosphere are incredibly small. Their size perfectly matches the short wavelength of blue light. They absorb the incoming beam and aggressively radiate the blue light across the entire sky. On hot days, large water vapor molecules flood the air. Because they are much larger, they scatter all wavelengths equally, blending the spectrum back together and turning the sky a hazy white. During a sunset, the light has to travel through a much thicker slice of the atmosphere to reach you. The nitrogen and oxygen molecules scatter the shorter blue wavelength so intensely that the blue light completely vanishes into space. Only the longer, unscattered red wavelengths survive. The color you see above you is a real-time atmospheric map. It visually plots the size, density, and distance of the invisible particles suspended over your head. All of these external physics dictate how light behaves in the environment. But to perceive them, your own eye must harness those same physical laws. Human vision relies entirely on biological refraction. Look at this cross-section of a healthy eye. The biological lens must bend the incoming light rays just enough to make them converge at a single, sharp focal point directly on the retina. But structural defects interrupt this process. In a condition called myopia, the eyeball is physically elongated. The light rays converge and focus too early, leaving distant objects blurry by the time the light actually hits the retina. We fix this structural failure with a concave glass lens. Placed in front of the eye, the glass pre-spreads the incoming light outward. This forces the natural lens to push the final focal point further back, landing it exactly on the retina. Hypermetropia creates the opposite problem. A shortened eyeball causes the light to focus too late. blurring nearby objects. Here, the fix is reversed. A convex lens pre-bends the light inward early, ensuring the rays don't overshoot the back wall. By tracking how light travels, bends, and breaks apart through physical matter, we mapped the mechanics of the visible universe. And by applying those exact mechanics to curved glass, we engineered the ability to force that universe into perfect, sharp focus.